Hello, Stats Cram Squad. Today I am super excited because we are finishing the curriculum today. That's always, as an AP Stats or an AP teacher, period, when you finish the content, you feel accomplished. So those of you who have been hanging out with us on Saturday afternoons, Sunday afternoons, Tuesday evenings, and all in between, hanging out on the Discord channel, congratulations. After today, you will have completed the AP Stats curriculum, and then is where we really get into reviewing, looking at the test, looking at the format, and all of that stuff, which is what's coming over the next few weeks. So today, we are going to cram, and when I say cram, I mean cram 2 units into 1 hour, units 8 and 9. And the reason why I did this is because both of them are accommodated between 2 to 5% of the AP exam, whereas the last 2 units together, units 6 and 7, account for like 40% of the AP exam, a huge portion. Okay, I think it's like 15%, 15 to 22% a piece or something. I'm not sure. I just know it's a lot. So I definitely wanted to break that up into 4 streams and these into 1 stream. I think we can focus on the type of problems that are going to be on the AP exam with a kind of a broad brush and prepare you for what's to come on the AP exam. Basically getting more bang out for our buck for the 11 streams that we are doing. So that was kind of the plan behind that, but we are definitely going to be moving through some content pretty quickly. Okay, so as always, it's recorded. Just be aware of that. And I think the video from Amanda is going to work today. So let's see.
What up, AP students? It's Amanda here from Fiveable. We are literally giving away $100 to pay for your AP exams to like 50 different students. How do you do it? Easy. You just gotta post about the AP experience on social media, on TikTok, Instagram, or Twitter. Use the hashtags YesWeCram and with Fiveable, and tag at Fiveable. So one person will win every single day, and this is how you can win. It is going to be a group of students who actually judge the winner. They will pick the winners, and this is how they're going to choose. It has to capture the AP experience. Do they look at that post and think like, that's 100% what this feels like? Is it creative? Is it funny? Does it have a really awesome song in it, or really good use of some sort of meme? Anything? Do we see creativity and engagement? How many likes do you have? That literally is going to help you win. The more likes, the more likely you are to win. And then finally, does it incorporate Fiveable? Is it in the caption, what you're wearing, in something that you're doing? How have you incorporated Fiveable into it? So this is how you can win. A couple of quick notes. Make sure you follow Fiveable so that we can DM you if you've won. You can post as many times as you want. You can post today, tomorrow, every day, as many times during the day as you want, but you can only win once, so keep that in mind. And finally, some of our best social interns came from this contest last year. So if you're really awesome at social media and you're looking for an internship, show us what you've got, because we want to hire you. So I can't wait to see your posts. See you on the flip side. Good luck on your exams. Talk to you later.
Woohoo! All right. It does appear like that worked that time, so I am excited on that. One thing I did want to mention before we
see you on the flip.
Whoa, didn't mean to do that. One thing that we are going to sort of be moving to as we prepare for the 5-hour cram finale is, instead of using the Vimeo chat will be off for the 5-hour cram. We are going to be using the question and answer feature on the Fiveable website. So you're all watching the video embedded. Okay, I can see Sanders already posted there to leave your questions, and we'll answer those. So we're going to be using that as opposed to the Vimeo chat. That way it is available for the replay. So just be aware of that. We'll still be looking at the chat for Vimeo today and also next week, but just be aware that for the 5-hour cram finale, that chat will be turned off because we're expecting hundreds of people. Can't keep up with that. So use the post feature in the Fiveable website. Okay, so you can see that right down below your video screen on the fiveable.me website. Cool. All right, awesome. So, see, I don't.
What up, AP students?
No, don't play that. There we go. So socials again. Think Fiveable. Okay, that's the that's where you're gonna tag your videos. So upcoming events next week on May 7th. It's a Friday at 6 p.m. Eastern Time. We will be doing free response tips and tricks. I think that's going to be a very valuable stream. Okay, it's one that I'm requiring my personal students to attend. Actually, they'll watch it as a replay that following Monday probably. Trivia for Unit 8 and 9 is tomorrow night. That'll be great too. Multiple choice is really where we're focusing at with this particular unit, or these two units. And then our 5-hour cram finale, Sunday, May 16th. I think you almost could sort of think of the free response tips and tricks kind of leading into that. It's going to be a very broad overview. Definitely not going to be able to practice as much on next Friday, but it kind of helps lay that groundwork as well. So definitely those two streams are, to me, very, very valuable. So yes, we have one today and then one Friday, May 7th, okay? And then the trivia on Sunday, which is tomorrow, okay? All right, so in this stream, we are going to focus on the chi-squared distribution. What does that look like? How is that different from the normal distribution and the t-distribution like we've looked at so far? What are the different chi-squared tests? How do we run those tests? And included in that, and I saw this in the Discord chat right before we hopped on here, expected counts is one of those things that you definitely need to be aware of how to do. How do we calculate the test statistic? If I'm thinking multiple choice questions, those are the three topics that I would expect you to see a multiple choice question on. Which chi-squared test to run in a particular instance, calculate the expected counts, and calculate the test statistic on multiple choice. I would those are the most common ones that seem to show up, so that's where we're really focusing. We're also going to flip and look at linear regression t-test from the viewpoint of a computer output, because that's 99% of the time what you're going to see on free response or on multiple choice. So probably not likely you're going to run a full test. Also not likely you're going to have to do it in your calculator or anything like we have with the other tests, but we need to know that computer output like we've done with linear regression back in Unit 2. Okay, and then we'll look at a few examples kind of along the way as we have time, kind of with each section there, Unit 8 and 9. All right, so one of the things that we need to be aware of is that chi-squared is kind of like the next step in categorical data. So in the Vimeo chat, which distribution do we typically use for categorical data so far? Somebody remind me what distribution we have used up until this point for categorical data or proportions. Yes, lots of Z's. Exactly, that is correct. We are going to use the Z distribution, so either a Z interval or a Z test. And in the calculator, you have to specify that it is a one prop Z interval, one prop Z test, etc. Okay, so that was what we used when we had either one proportion or two proportions that we were comparing to each other from like two samples. Okay, so almost like a two sample test for proportions. So what we're going to do now is we're going to expand that toolkit for categorical data, and we're going to add in chi-squared, which in the real world is probably a lot more likely that you would see. I've had more people come to me in like grad school doing research projects asking questions about chi-squared as opposed to Z intervals and Z tests. Okay, so I think chi-squared is really important. I don't have the same sentiment for Unit 9, but it's on the AP exam, so we have to do it. But chi-squared is very important in the in the real world, and it uses that to compare more than one proportion. So more than one variable or more than one category among one variable, and we'll look at those as we continue on. So one of the big things that is important for the chi-squared distribution is the number of degrees of freedom. That changes the curve, it changes the distribution drastically. And that's what you can see here in this graphic. I'm going to do just slides so you can see that a little bit better. So the yellow distribution is when we only have 1 degree of freedom, which typically means we have 2 categories in our variable, which is not typically, that means it's binary, so you could run a z-test. I can't think of anything off the top of my head where that would not work. And you can see it's strongly skewed right, that yellow line there, okay? It is, and biggest thing here, notice this curve is not normal. So when we're going into our conditions in a little while, we are not checking a normal count. Okay, it's not at all what we're doing. So then you see as you get 2 degrees of freedom, all right, it kind of mellows out that skewed right, still strongly skewed right, the green curve here on our graph. There's no hump in the graph, it's just all the way tailed to the right. And then you get the teal with a 3 degrees of freedom, you get the little hump with a skewed right, and then as you continue on and on, the last one, a degrees of freedom of 9, which would mean there will be like 10 categories, which we'll get to in just a second. It mellows out a little bit more, okay? It's going to look more symmetric and more spread out, I guess, stretched out, not just all shifted to the right side. All right, so that is what the chi-squared distribution looks like. Notice it's not at all normal. It's also not at all a t-score. So a t-score had the degrees of freedom, but regardless, it still looked somewhat normal. Just maybe more stretched out or more squished in. Now, what is another difference about our chi-squared distribution comparing it to our normal distribution or t-score distribution? In the chat, what is another difference there that we can see based off of the graphic you can see on the slides? Okay, what about, okay, so R says way flatter, which is true. Okay, it doesn't have that huge bump in the middle until you start getting to the other ones, and even then it is more flat. And the numbers for X and Y. Okay, be more specific on the numbers for X. That's what I'm really focused on here. What are different about the numbers for the X-axis for chi-squared opposed to normal on the X-axis? There's a lot of them below 1, that is true, but all of them are the x-axis, okay, so the horizontal axis from left to right. So for chi-squared it goes from 0 to 8 for basically all of them. So think to a normal curve. Where is the middle of our normal curve going to be at? A normal curve wouldn't go above 10. Chi-squared might go above 10. Normal curve barely ever would go that way. So the normal curve is centered at 0. This one is not centered at 0. In fact, 0 is as far left as it's going to go. Okay, so yeah, the middle here, about 4 or so. So what I was looking for is that the chi-squared value is always going to be positive. Okay, so whenever you're calculating a chi-squared test statistic, which you know is going to lead you to get a p-value, our p-value is going to be the area underneath these curves, okay, well, depending on which curve it is, degrees of freedom. But your chi-squared test statistic is always going to be positive. Whereas if we had something on the left tail of a z-score or t-score, it would have been a negative test statistic, a negative z-score, negative t-score. Okay, and we'll see a little bit later on the formula for chi-squared why it's always positive. So keep that in mind. Chi-squared is always positive. The distribution is only in that quadrant 1. Okay, if you were to complete the Cartesian plane there, x, y axis, it's all in quadrant 1, whereas normal is left, quadrant 1 and 2. That's a really important distinction to make. Okay. All right, so previously we were limited to only having one variable for categorical data and 2 categories, okay? Either you were or you weren't, okay? Thinking to maybe, I think we did the example with the plants a few weeks ago, the coccia plants. And did they die with the herbicide or did they not die? So there's 2 options. Either they died or they didn't die. What was the probability that the weed died with the weed killer? Okay, so it was binary. Okay, and that was only one variable. It was the plants, alive or dead. Okay, 2 options. That's it. A lot of times we also look at things like drug trials. Placebo. Did it cure the disease? Not cure the disease. So that was the one variable we were looking at. Now we might have had 2 groups. But there were only 2 categories. Either you got the disease or you didn't get the disease. You were healed of the disease, you didn't. Okay, so we were limited to that. With chi-squared, it opens up multiple options. So for multiple categories within one variable, okay, and testing data with 2 variables. So maybe we want to look at what proportion of people taking a medicine are cured of the disease, and if that has any effect based off of their age. Okay, were they below 45 or above 45, or even we could split it up even more if we needed to, because we can do those multiple categories. So chi-squared gives us that option of looking at 2 variables and if they are correlated within each other, among categorical data, of course. Whereas before we were limited to maybe 2 populations, and definitely only 2 variables. It had to be a yes or no category within that variable. All right, so here are the 3 types of tests that we are going to look at running. Okay, the first one is a chi-squared goodness of fit test. It is used with only one variable and multiple categories. So we can't have 2 variables there. We could do something like colors of M&Ms. All right, so if we take M&Ms and we separate them, all right, we could run a test, because with a z-test, we would have to split it up something like blue M&M, not blue M&M. Okay, so make it into 2 categories. And we could do that, but that doesn't really tell us much. It only can tell us things about the proportion of blue M&Ms. However, with chi-squared goodness of fit, we can look at all the colors. So blue, orange, yellow, green, brown, red, maybe. I think I might have made some colors up. I'm not sure on my M&M colors. Need to brush up on that a little bit. With that being said, your null hypothesis for a chi-squared goodness of fit test is always going to be the proportion of the first category equals whatever. And that's like your claim, okay? Remember, null is dull. So if you have someone telling you that, a recent study shows that the proportion of the colors of M&Ms are equal across all colors, which we know is not really true, then you would put P sub blue, little bitty blue, equals 0.2. P sub green equals 0.2. And do that for all the colors. So your null is what is ever going to be in agreement of what you're testing against. Okay? So chi-squared goodness of fit, your null hypothesis is it's going to be in line with whatever the study shows, whatever the claim shows. Sometimes it might tell you that two things are equal, and if it tells you that two things are equal, then you are going to want to, take 100% and divide by however many categories there are. Colors, M&Ms, I think there's 5. So it would be 0.2, 0.2, 0.2, and so on. And then your alternate hypothesis is that at least one of those is incorrect, which with M&Ms, we probably would find that if we took a random sample of M&Ms and looked at the proportions. The proportions of our M&Ms would probably not be 0.2, 0.2, 0.2, 0.2. It would be different. There would be some sort of difference somewhere in there. So then we could say that the article, we have reason to doubt the article, but we can't really pinpoint exactly without some further investigation which one of those is the culprit to making them not equal. But we can say at least one of them's off. And, what's one of the things in math? If you make a statement of 5 things are true, and someone has a counterexample for one of them, your whole thing is false. Okay? You only have to disprove one of the aspects of someone's statement to prove that they're incorrect, and that's what we're looking at doing. All right, so that's chi-squared goodness of fit. It's going to come in the form of a 1-column table or a 1-row table. Okay? The next one is a chi-squared test for association. Sometimes it's listed as tests for independence. That is when we have 2 variables, but only 1 sample. So basically, we took one sample of 1,000 people and asked them 2 questions. What's your age? So we're going to put them in a category by age. And have you received the COVID vaccine? Yes or no. All right. And then we can look and see if age is associated with whether or not people are getting the COVID vaccine. Okay. Now that I think we've had a decent amount of time where 16 and older has been available, and we're going to see, are younger people more hesitant to get it? Or older people, how can we reach out to this group that's maybe not getting it as much? Okay. Which would be a good study for healthcare professionals to do, I think. But the big thing here is that it's 2 variables and 1 sample. So if you're looking at what your data is going to look like, it's going to look like a 2-way table. Okay, both of these next 2 tests are going to look like a 2-way table, and I'll clarify the difference in just a second. So your null hypothesis is going to state that the 2 variables are not associated. So in other words, the likelihood of getting a COVID vaccine and age are not associated. That would be your null. Which remember, null is dull. I really love that. My students have adopted that over the past few weeks, and I think it's helped them. Sandra shared that in the past few weeks in the chat, which was great. If age has nothing to do with whether someone is hesitant to get a COVID vaccine, then, there's nothing there. There's no study to support that. Let's move on and try to figure out something else. But that is the null. It's dull. There's nothing special going on. There's not that aha moment for a scientist to step in and try to adjust things. So nothing is going on. All right, so it's that they're not associated. Or you could say that they are independent, because remember, independent means 2 things are not influencing. That can be a little bit confusing. Whoop whoop! Stats 2 professor coming in for the win there. That's a great saying. I will continue using that in years in the future as well. So then your alternate hypothesis is simply that they are associated. Just make sure you include context. Again, you're probably looking at a multiple choice question here. So context would probably already be there. Or you would read one that didn't have context and know that you would pick the one that did, hopefully. Okay, so then the other test also comes from a 2-way table. I'm going to turn on slides only. That gray and white's a little bit hard to see. Hopefully that helps some. It is used, so chi-squared test for homogeneity. That is used with 2 variables, but also you have two samples. So let's say I wanted to compare people in Alabama to people in New York and whether or not they are over 16, wanted to get the COVID or have gotten their first dose of COVID vaccine, whatever. Okay, so that's two samples. I asked 1,000 people in Alabama and 1,000 people in New York. And something in the problem will cue you that it was two separate samples, two separate populations I'm comparing. The overall outcome is almost the same as the test for association, but you're not looking necessarily that two variables are associated. You're looking if two populations are same or different. So your null hypothesis is that the two population distributions are the same. All right, the distribution of people who want to receive the COVID vaccine in Alabama is the same as the distribution of people in New York. Okay, again, null is dull. There's nothing special going on there. They're equal. There's nothing we need to do to reach out more to one of the two populations. All right, and then the alternate hypothesis is that the two population distributions are not the same. It's just the opposite, okay? So the big difference here, and this is that it's really easy to determine which of chi-squared tests to run if you remember these three things. A goodness of fit test is going to be one row, one column, depending on which direction it is, it doesn't really matter. The other two are going to be a two-way table. Think back to probability in Unit 4, a two-way table. Independence is one sample taken, a random sample of 250 adults. Okay, and it will also usually say, is there an association between blank and blank? That's the cue. Is there a convincing evidence that there is an association? That should be chi-squared test of association if it's a two-way table. And then the chi-squared test for homogeneity, that's when there's two samples. A random sample of 250 adults from Alabama and a random sample of 250 adults from New York. There's two samples you are comparing, not just two variables. All right, so two-way table with two samples, homogeneity. Two-way table with one sample where you ask them two questions, that's the test for association. Took me a long time to wrap my mind around that, but it's really not as complicated, I think, as I was making it out to be in the beginning. Okay, so the first thing you want to do is state. Make sure you identify which test. Sometimes we put that in the do section, which we'll go over in a minute. So again, look at how many variables are being tested. Is it a one-way table or a two-way table? And if it's a two-way table, look at how many samples or populations are in that question. That's the big separation there. Write your hypotheses according to what we had on that previous slide. To plan, they are a little bit different for chi-squared. Now there's my Alabama lingo coming out. They're a tad different. That's something we say here for a little bit different. Random, same as before. Quote the problem. If it's an experiment, make sure you specify random assignment, not random experiment. Okay? Or not random selection. So if it's an experiment, note the random assignment. Otherwise, an SRS of 250 adults, just quote the problem. You're good to go on that condition. Independent is the same. All right, now we do not have normal because remember it's not a normal curve. It is the chi-squared curve, which is that strongly skewed right, all positive curve. You have to make sure that your expected counts are all at least 5. All right, so back to our M&M's example. If all colors are different and I take a random sample of 100, that means that I should have 20 blue, 20 red, 20 green, 20 yellow, and 20 brown. Okay, so I need to state that I expected to have 20 of each color, which is more than 5. When you're doing one of the other tests, essentially you're just doing it in the calculator. It's the row column times the column row total times the column total divided by the total. So there's more on that in the study guides you can look at to do that. But you can also do it in the calculator pretty easily. So if it's a goodness of fit test, you take your sample size and multiply it times all of your null proportions. If they're all equal, as long as the one is more than 5, then you're good. If the proportions are different to add up to the 100%, then do each one individually times the sample size. For independence or association or homogeneity, you're going to look at matrix B in your calculator. Basically, to do that test, you're going to enter matrix A as your two-way table, leaving off your totals, and then it will automatically generate the expected counts for matrix B. Yes, absolutely. The Unit 8 study guides on the Fiveable website go into great detail on that. I'll try to link that before we leave here today. So yeah, the calculator will do the expected counts for the two-way table tests in matrix B. All right, you have to write them down to receive full credit for that condition. Just write down the new two-way table and say all of them are at least 5. Okay, if you were to see this on free response, which I kind of doubt, but it could happen. It has happened in years past. But now they've clarified things and they've shrunk this unit down a good bit. All right, so do. For goodness of fit, you're going to choose the chi-square goodness of fit test in the calculator. It's right there, GOF. Okay, remember that's a one-way table. Goodness of fit, one-way table. Your degrees of freedom you have to enter is the number of categories minus 1. Going to our M&M example, there are 5 colors of M&Ms. The degrees of freedom would be 4. Okay, there will be 5 entries into our table. It's that minus 1. Okay, you want to make sure you write down your chi-squared test statistic. You want to make sure you write down your p-value. As always, you need your test statistic and your p-value. And remember, if you get totally lost, but you know it is an inference question, make up a reasonable p-value and then conclude accordingly. All right, you can get partial credit off of that. It's a huge step in just preparing for the exam. If you get stuck, but you know it's an SPDC inference question, do the parts you do know. And if you don't know how to get a p-value, make one up that makes sense and then conclude correctly. You get the point for the conclusion, even if your p-value was totally wrong. I've had students do that in the past and it worked out well for them. If it's independent or homogeneity, you have to specify on your paper which one you're running, but in the test, in the calculator, it's the same thing, chi-squared test. All right, so your degrees of freedom is the number of rows minus 1 and number of columns minus 1. The chi-squared statistic, again, that it spits out, and the p-value that it gives you as well. Okay. All right, so in the chat, I see some discussion there I definitely want to address. So Ryan says, if we make a p-value, we use 0.5. All right, and Sandra is correct. If we are not given an alpha level, which is what we compare the p with, use 0.05, 5%. That's the standard across the board in the statistics world, what we compare the p-value to. So if you can't figure out how to get a p-value and you're trying to make one up to get to a conclusion that makes sense, okay? If the data to you looks significant, like, whoa, those two variables are clearly impacting each other, then make up a p-value less than 0.05. So it leads to a conclusion that there's some sort of association, okay? If you look at the data and they look essentially the same, they don't really look that significant, like, yeah, I don't think age has anything to do with whether or not someone's reluctant to get the COVID vaccine, then make your p-value greater than 0.05. Make it 0.11 or something, okay? And then you would conclude that you failed to reject the HO. There is not significant evidence that the age plays an impact in someone's reluctancy to get the COVID vaccine, okay? So that's kind of how I would break things down there. All right, I'll swap screens again. All right, so this is the formula for the chi-squared test statistic. It is likely you will have a multiple choice question on picking out which one is the correct one. And it's pretty easy. Observed minus expected. This is what your actual sample gave you. Expected is what's in your expected count. And you square that. That's why all chi-square values are positive, because you're squaring everything. Square negative, it becomes positive. and then dividing by the expected. So look at the multiple choice options and make sure that the second number in your sum, in all parts of your sum, because you're adding all those up for each input to your two-way or one-way table, make sure the second number up top matches the bottom number. Okay, that's really the biggest thing. You generally can, if you know the general format of the question, which we'll look at some examples on the 5-hour cram finale on the multiple choice for these, probably in the last hour on the mixed review. The last number up top should match the bottom number. Okay, and you should be adding up all the different outcomes. Okay, oh, I don't want to do all this. Let's see. Time-wise, we'll kind of move through this pretty quickly to get to the regression. So the question is, a recent article from Candyman International claimed that Skittles colors were evenly distributed amongst the colors. All right, so red, yellow, green, purple, and orange are all equal, kind of like we've been talking about. To test this theory, Mr. Taste the Rainbow has gathered a random sample of 500 Skittles and found the following numbers. And what we have found is that the red, he had 120 reds, he had 90 yellows, he had 100 greens, 110 purples, and 80 orange. Okay, now do these seem to all be equal to each other? Not really. So if you were given this question, is there convincing evidence that the proportions of M&Ms are not equal? I would say yeah, like those are pretty good different, okay? So I would pick a p-value that was low, all right? And what we would do, this would be a chi-square goodness of fit. All right, the reason why is because we have one variable and the multiple categories. I can't just do a 2-prop z-test or a 1-prop z-test because we have 5 colors, not just one color. Okay, we're not just looking at red, not red. We're looking at all the colors. So it is a chi-square goodness of fit test. So your hypotheses would be the proportion of red, notice I used a meaningful subscript, is equal to 0.2 because it says that Candyman International said they're evenly distributed. P yellow equals 0.2, P green equals 0.2, P purple equals 0.2, P orange equals 0.2. The ha is that at least one of these is incorrect. To calculate the test statistic, okay, I was going to share my screen and kind of work that out, but I definitely want to get to the regression stuff. All right, so we would expect out of 500 Skittles to have 100, 100, 100, 100, and 100. So what you would do is it would be observed 120 minus the expected, which would be 100, squared, divided by 100. Okay, I can sort of type that in the chat. So observed minus expected squared divided by 100 plus 90 minus 100 squared divided by 100, etc. Okay, so that's what your you can see in the chat there. I just put that on there. It is unusual to have a free response question on one of these, considering it is just 2 to 4% of the exam, and that's why we're kind of moving through it quickly. But it would be a sum of all 5 colors. You would have 5 numbers being added up, and 120 minus 100 squared divided by 100, and so on and so forth for each color. The only reason why we're subtracting 100 and dividing by 100 on all parts of our statistic here is because the claim was that they were all equal. Okay, which color contributes the most to the test statistic? That would be red and orange, because those are both equally distant from 100. Okay, there's a difference of 20 here, so 20 squared would be 400 divided by 100, which would be 4. So its contribution to the test statistic would be 4. Orange, 80 minus 100 is negative 20, squared is positive 400, divided by 100 is also 4. So both of those contribute to that summation equally. And you can see that on your calculator, which we will go through and do. Okay, there we go. So to do this in the calculator, I need to first of all enter my data. So my L1 is going to be my observed, 120, 90, 100, 110, and 80. And then my L2 is going to be my expected. And when we run the test in a minute, it'll cue you for that. So you'll kind of be reminded. All right, and then go to Stat, go over to Test like we do for all of our inference procedures. Go up to option D, which is chi-squared goodness of fit. Observed L1, expected L2. Degrees of freedom is not 5 here. It is going to be 4 because we take the categories minus 1. And then I'm going to calculate or draw. I'll draw just so we can see the... So we get the chi-squared curve and we get our p-value right there. So our chi-squared value was 10. So we would need to write that down. We would also need to write down our p-value, which is less than 0.05, which would lead us to reject the null. Okay, so this is where it's at on the, so here's the 0 on the chi-squared curve. We're at 10. The odds of getting a value of 10 or more, assuming that the null is true, is a 4% chance, which is less than 0.05. Okay, I know I went through that really quickly, so I do apologize. So there's our p-value and our chi-squared, and then we would do our conclusion. Okay, since 0.04 is less than 0.05, we reject the null hypothesis. There is convincing evidence that at least one of the proportions of Skittles colors is different than the others. So we compared our p-value to 0.05. We made our decision about the null based on we have okay, and if we are not siding with the null, then we are going to side with the alternate. That does not mean we accept the alternate. We are siding with the alternate, okay? Which means there is convincing evidence that at least one of them is different than the other. Never say accept. That's why I'm using the term side. Which one are we siding with? We're siding with the alternate based off of our p-value. Based off of the p-value, we don't side with the null. Therefore, our second alternate, there is convincing evidence of that alternate hypothesis. Okay? And there's our computer output, or our calculator output. All right. Fail to reject instead of accept. Exactly. So if we're siding with the null, we want to state that we fail to reject the null. Just to clarify that. Never use the word accept. If you're looking at a multiple choice question and you see the word that our p-value would lead us to accept something, exit out, it's not the answer. Okay, move on to, you can narrow things down. So the biggest thing with multiple choice questions on the AP exam is process of elimination. My students this week, we've done a lot of those, and they've gotten a lot better at multiple choice. I won't say great yet. We're still working. We still got a few more weeks. But they've gotten a lot better at it using that process of elimination. I feel like I've gotten better at it as well, understanding the content from that. Okay, so linear regression t-tests. I know we ran through chi-squared extremely quick. Look at the study guides. Also, on the 5-hour cram finale for sure, we will do some of the multiple choice questions like I expect you to see. Okay, so we'll definitely hone in on that. So linear regression t-tests. All right, I won't get on my soapbox about why I don't really care for this this unit, but it is there, so we have to learn it. So we are focused on the slope. If you're doing some sort of inference with linear regression, the y-intercept aspect does not matter. So what we're looking at is, does the slope differ from 0? AKA, is there a correlation? So the null hypothesis here is that our two variables are not related. which if they're not related, the slope of our regression equation, our least squares regression line, is going to be 0. That's why your null is going to be that the slope is 0. Okay, so your null hypothesis is that the slope is 0. Your alternate hypothesis, depending on if it's a positive or negative correlation, is that the slope is not 0. Maybe it's just that they are correlated. Maybe it's that there's a positive correlation, so the slope is greater than 0, negative correlation less than 0. And the symbol for slope is the Greek letter beta, the capital B, beta, so the B with the little tail. So if you see that, that's a regression inference question, which again, 5-hour cram finale, we'll look at multiple choice questions from that. So here's what our computer output looks like. This is the same question we used in Unit 2. So it might look a little bit familiar. Remember, you draw your boot, okay? Slope is the bottom line. I've never seen one where it's not the bottom line. It's also the one that has the context. Y-intercept is the constant number. So we focused on these. Remember, that's your slope. You need to know that interpretation. This is your y-intercept. You need to know that interpretation. We don't use r-squared adjusted. We use the r-squared regular. But what we're going to focus on now are mainly these two values, the t and the p. Typically, the p is really what is the money maker there. All right. So again, there's our valuable information. I'm not interested in the inference values for the y-intercept. We don't do that in AP Stats. Apparently it's important because people print it on computer outputs, but it's not what we're focused on. Okay, so the big thing here is that our p-value is less than 0.05. It's 0.02. So we reject our null hypothesis. Okay, so we reject the fact that the slope is 0. We have significant evidence that there is a correlation between the number of sick days given by the company and the wellness visits taken by employees. Okay, so somebody in the chat, tell me something else about this computer output that supports that conclusion we just made. What is something else that supports that conclusion in all of our computer output there? Yes, besides the p. So in the grand scheme of our linear regression model, our scatter plot with our line through it, okay, we've determined from the p-value that there is a correlation because it's less than 0.05. Okay, but what else in the computer output says, yeah, those two things are highly correlated? Okay, the slope is 0.96 and not 0. That is also true. But I mean, we could have a positive slope with the line, with the points still all scattered out. There's something else that tells us, hey, this is a good correlation. Standard deviation varying so little, that's also true. The r squared, yes! Okay, so the r squared is pretty high. So remember, the r squared, okay, here would be the interpretation for that. 81.7% of the variation in wellness visits is explained by its linear relationship with sick days allowed. Okay, that is your can statement. We use context. 81% of the y is explained by the x, by its linear relationship with the x. Okay, so if 81% of the variation in y is explained by x, all right, well that means we've got a good linear relationship. So if we have a good linear relationship, there's probably a correlation, aka the p is less than 0.05. Okay, meaning there is a slope. So that is to me, that's one reason why I don't really care for this unit, is because we can come to the same conclusion using that r squared value that is more likely to be used. Okay? The r squared tells you what so it tells you how much of the response variable, which is the y, is explained by the x. Okay, it also can lead you to that r value if you take the square root. Okay, so r is 0.904. Okay, if you take the square root of it. Also, the r value is positive because the slope is positive. Slope is 0.96. So if we have an r value of 0.94, remember that means that there is a strong, because it's more than 0.8. It's positive because the slope is positive, and linear because we have an r value. We only do linear in AP Stats. Very, very, very unlikely you will have something that's not linear on the AP Stats exam. And in our limited time, really more bang for our buck, we're just not really as concerned about that. So there's a strong positive linear relationship between sick days and number of wellness visits. Okay. So that's our R interpretation. That's typically what we use. You probably did that in Algebra 2 or maybe geometry. In Alabama, we just put that into geometry. Understanding what that R value means. It's that value between -1 and 1 that tells you how good the model is. How correlated is it? Is it a strong correlation, a weak correlation, etc.? So from the R squared value, we can see that there is a strong correlation between those two variables. So the p-value really just strengthens that. Okay, it states the same thing. It states that very unlikely that the slope is 0. All right, there is some sort of correlation between the two. And again, since our sample slope, okay, this is a sample slope. Think about it this way. We only have a handful of data that generated this equation. It's not the population of everybody that works a job with sick days and wellness visits. Okay, it's just a small sample. That small sample gave us a slope of 0.96. All right, and based off of that sample and that p-value, if we assume that the population slope is 0, the probability of getting this strong of a slope with our sample size, whatever it may have been, is 0.02, which is a really low odds. Since it's a low odds, we reject the null that the slope is 0, and we pretty much have proof that the population value is not 0. It's greater than 0. There is a positive correlation. Okay, so I think maybe I'm understanding this more myself. This R squared value is for the sample. So from our sample, we can see that 81.7% of the variation is explained by those two things. Okay, which is good. However, we can't quite jump to conclusions about the population without looking at what the probability of getting that model is if there is no correlation. Okay, so that's where the p-value comes in. The t-score is where it falls on the curve. I don't have the actual data to put this in, I don't think. It is linear regression t-test here, option F. Yeah, I don't have the data to put in. So see that beta there? Let me share my calculator screen. So beta, that is the symbol for slope. Okay, that's what we're typically using there. So let's see. Let me try a different one. So the t-score is 4.12, which means that's where it falls at on the. That's its t-score. Observed minus expected divided by standard deviation. Okay, it's a good ways away from 0. I'll tell you what, I can do this. Distribute TCDF 4.12 to infinity. Degrees of freedom. say 98 because I'm saying a sample size of 100. Okay, it's essentially 0. Well, let me draw it. Dang. I was hoping I could draw it to show you what that t-score means. Okay, think the middle of your curve is at 0, and normal curve-ish, because our degrees of freedom would be high here. We would have to have a sample of a good bit to be able to pull from that. So middle of our curve is 0, and then if it's normal, 3 standard deviations out. We're at 4.12. Okay, so we're at 4.12 all the way over here on the right. The probability of being at 4.12 on a t-curve or a normal curve or above is really small, so 0.02. That's where that t-score connects with the p-value there. Okay, for degrees of freedom, it's generally sample size minus 2 on regression t-tests. That's in the study guides as well. It goes into more detail. It's just not such a big topic that we don't talk about it as much. Okay. So that's the correlation. The R-squared value is how well our sample was correlated. And you, of course, can get the R value by taking the square root. And then if it's more than 0.8, it's a strong correlation. So our sample is strongly correlated. And then the p-value just strengthens that and allows us to go outside of our sample to the population. Well, if there's really no correlation, there's a 2% chance that we were able to get this sample that's so highly correlated. Therefore, probably not. They are actually correlated. The slope is not really 0 for the population of everybody x and y axis plotted. Okay, so for a t-interval, I've seen this on multiple choice questions as well. Again, we got our boot. So remember, for a t-interval, here's your parts of a confidence interval. You have your sample slope, which is 0.96, plus or minus your t-star, not 4.12, okay? And then times your standard deviation. All right, the 4.12 is the t-score for our sample. All right, so that is the t-score that would have a tail of 0.02. But if we're doing a 95% confidence interval, the t-score is going to have a tail of 0.025. So you have to calculate that t-score using the the calculator. That would be inverse t. It's also on your formula sheet as well, which we'll look at next week. All right, so the area, if it's a 95% confidence interval, would be 0.025. Your degrees of freedom, let's say there were 100 people, would be 98. You subtract 2. All right, it would be 1.98. So your confidence interval for this, if it were 100 people in our sample, would be 0.96 plus or minus 1.98. Oh, I forgot to swap my calculator there. Okay. So you can see how I did that. So inverse t, we know the area for a 95% confidence interval in the tail would be 0.025. Our degrees of freedom is 98 because it's n minus 2. It's the only one where degrees of freedom is minus 2. And like I said, I'm assuming it's a sample of 100 people. So 98. And that gave us 1.98. Okay. So our confidence interval would be 0.96, our sample slope, plus or minus our 1.98 times 0.12. The big hole that you can fall into, that I fell into when I was originally working out that question that I'm referring to that I saw earlier this year, is that I thought the t-score would be 4.12. But that is the t-score for our sample. We're looking at a t-score for our confidence interval, which means we know the tail is, like I said, 95% might be 0.025. Okay, so it's going to be different. So yeah, that is the confidence interval formula is the same. It's a t-score. You have to find that based off of your degrees of freedom, n minus 2, and your whatever confidence interval you're doing, and the tail probability. Okay, but the sample slope and the standard deviation are the two things that are in your boot. Okay, same general format. Your statistic plus or minus your critical value times your standard deviation or standard error. All right. So yeah, there you can see that everything worked out. Okay, I did it off a sample size of 398. So if you go in the calculator, I'll change that to, instead of 98, I'll change it to 398. .96. Okay. So yeah, and again, it's probably going to be a multiple choice question where you have to identify the 3 parts of that confidence interval. That's how it was when I saw it from an old exam. Sample slope from your computer output, your t-score from the calculator or from your formula sheet, and then your standard deviation from the computer output. All right. Right at 1 o'clock, or 1 o'clock where I'm at, so right at 1 hour. So the big things you need to know, and we will go over these multiple choice questions on the Cram finale, absolutely, because that's where you're going to see them more than likely. Be able to differentiate between the 3 types of chi-squared tests. Okay, one column or one row table, a one-way table, is goodness of fit. A two-way table with one sample is association. A two-way table with 2 separate samples that's making up either the rows or the column with clear 2 samples is the test for homogeneity, and you have to tell that when you're naming your test. Be able to calculate expected counts and check the conditions. The condition is that they're at least all 5. Be able to identify the chi-squared test statistic on the multiple choice not being worked out, so that's observed minus expected squared. Divided by expected. Number 4, the next thing, be able to identify the confidence interval on multiple choice from the computer output, just like we just did, the 3 parts of the confidence interval. Be able to conclude tests using that p-value. P is low, that means you reject the null. That means that there is convincing evidence that their 2 things are correlated. Okay, so the null is that the base, or capital B, not base, beta, is 0. AKA that means there's no correlation. That's your null is dull there. Okay, those are the 2 things from linear regression t-tests you would possibly see. Sometimes that's on free response, like the number 6, and I could totally see them giving you a computer output, having you interpret some of the normal stuff, and then also having you kind of see what the inference procedure would look like in the number 6 investigative task. Okay, so that is everything on units 8 and 9 that you need to know. For more multiple choice practice, trivia tomorrow night, Sunday, May 2nd, 6 p.m. Eastern Time, and then right after that is 6:30 for Unit 9. Also the 5-hour Eastern Time. Okay, so we'll definitely look at the multiple choice practice on that, and you can familiarize yourself with those. Okay. Keep the conversation going. Discord. We will be over there in a jiffy. That's one of those other things we say in Alabama. To take questions and answer those questions on the topics for today. Hope you all have a fantastic weekend.